Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Dr. Aditi Krishnapriyan, who is an assistant professor at UC Berkeley, where she is a member of Berkeley AI Research, Electrical Engineering and Computer Science, and Chemical Engineering. Her research interests include physics-inspired machine learning methods, geometric deep learning, inverse problems, and development of machine learning methods informed by physical sciences applications, including molecular dynamics and fluid mechanics. A former DOE computational science graduate fellow, she holds a PhD from Stanford University and in 2020 to 2022 was the Luis Alvarez Fellow in Computing Sciences at Lawrence Berkeley National Laboratory. Today, Aditi will talk about bridging numerical methods and deep learning with physics-constrained differential solvers. I'm sure she's going to give us a fantastic talk, so please have a high expectations. But before I pass the baton to Aditi, let me ask a one questions as usual, as a tradition of this DDPS seminar. So my question is for you, Aditi, is I happen to know one of your hobby is translating your language from one language to the another language. Why is that a hobby? That's my question. And what kind of language do you usually translate from, to, what other language? Yes.
Oh, yeah, I'm just generally interested in different language families and bridges between different language families, which tend to also be informed by migration patterns. So looking at completely different areas of the world and seeing what the overlaps are in language families is just a fun hobby to work on. It's gotten quite interesting now, especially with some of the LLMs and a lot of the improvement in translation.
Oh, that's awesome. And that's kind of related to the title of your talk today, the bridging numerical methods and the deep learning. Yes. So you like to bridge. Awesome. Okay. Stage is yours, Aditi.
Great. Yeah, thanks a lot for the invitation and the introduction. I was looking forward to giving this talk because I think a lot of the themes here, my impression is that they're going to overlap a lot with the backgrounds of people in the audience, which could be a mix of applied math, machine learning, physics, and so on. And so this is going to just be a general overview of what we can get from numerical methods that we've known for a long time, and a lot of the more modern machinery and deep learning that has obviously seen a lot of success, especially in the last decade or so. So a lot of this talk and a lot of the research that we work on is really motivated by this big question of machine learning potential in modeling scientific systems. And more specifically, a lot of these problems, I think, come down to how well you can model spatial and temporal behavior. So whether it's something like modeling fluid dynamics or some type of weather patterns, or even when you're looking at molecular systems, how did the atoms move over time? These are really all underlyingly represented by modeling spatial and temporal behavior of those systems. And I think there's so many applications where this is actually a pretty challenging task, where we have some really complex phenomena. We want to really understand all of the intricacies of that spatiotemporal behavior. And by doing so, I think this really unlocks a lot of insights in many, many different fields of science. So I'll briefly talk about what I think are some of the advantages that neural networks can offer for physical modeling. I think these can be a powerful tool to assist us in this task, while also keeping in mind some of the limitations or some of the things that we have to just know a priori or account a priori when we're developing these methods. So the first point, and one of the big advantages here, is after you train a neural network, when you actually go and test it or do inference on new problems, this is quite cheap because you've amortized the computation during training. And neural networks, as we've seen time and time and again, they're really, really good at approximating high-dimensional functions. And this starts to become really nice when we're trying to solve these scientific problems that are very high-dimensional problems and may have complicated solutions or ways to get to complicated solutions. At the same time, I think there's also some things to keep in mind, particularly with neural networks in the context of scientific computing. So how do they actually compare to these current mechanistic models or even experiments in a lab? So there's always going to be this cost of training, this cost of data generation. And because we have these nice models we've developed for many, many decades that came before neural networks, I think it's important to keep in mind these models themselves at the same time as we're developing new methods that are going to bring in this idea of machine learning. And the other point here, another thing to keep in mind, is the accuracy point. So it's not very useful if a neural network is really fast, but it converges quickly to the wrong answers. Since this is, again, something really important for scientific modeling, that we want something that is going to be in a decent ballpark, that's going to be at least a good initial guess to getting us to the right solutions. And then finally, I think this other point, again, important for scientific modeling, is this idea of reliability in methods. So a lot of the numerical methods that have been developed over the decades have really very strict reliability criteria, or have been really stress tested to ensure some level of reliability. And so can we actually keep that in mind when we're bringing in this component of machine learning into these problems? And so I'll start with a really example common scenario, and this is really going to be the basis of the rest of this talk as I describe some of the methods that we've been working on now that go beyond some of these common scenarios or some of these more toy examples. And in this example, this is some type of damping pendulum. So you might have some training data in the early part of this trajectory, and your goal is to predict the later dynamics of this system. And this could be governed by this very simple PDE. So this is a really toy example. So if you train a neural network on predicting only the points in your training data, so you train it by minimizing this loss function to match those training data points, you can see that it doesn't do very well when it's trying to predict the later time steps, even though it gets the early time steps that it's seen before quite well, which is what we would expect. But one approach here that I think many of you will be very, very familiar with is this idea that you could add that underlying ODE or possibly an underlying PDE as a soft constraint to the neural network loss function. And you essentially optimize over this. So you have that training data, but then since you have some form of the differential equation, this could be some type of conservation law, you add that to the loss function, and you essentially enforce that over all of the later points in the domain. And when you train with both of these objectives, you can see that in this case, it seems like it's actually fitting the later dynamics because you were giving some implicit information, some self-supervised or auxiliary information about the later time steps. And this is very colloquially known as this physics-informed neural network loss, where you have these physical laws that are enforced over points in the domain, so some discretization. So the one thing about this type of approach, on one hand, it's potentially a way to deal with limited data, or if you have some type of conservation laws you'd like to enforce, it's potentially one way to try to add in that type of information. But I think, as maybe many of you have dealt with, if you've trained some of these models, adding the physical laws this way doesn't necessarily guarantee the convergence or correct solution or enforcement of those laws. And often it takes a lot more beyond that to actually get some type of convergence property. And this is just a simple example of a convection problem where you have just this 1D PDE, as you increase this wave speed parameter, you can see that this type of training doesn't converge very well to the later time steps. So the left-hand side is this actual solution, and the right-hand side is what would happen when you train the model and then predict with this solution. So that brings me to, yeah.
Aditi, there's a
Yeah.
question on
Sure.
slide 7. Do you want to answer that first?
Oh, sure. I actually can't see the screen.
Yeah.
Do
What
you have
would
questions?
so what Pearson asked? What would happen if you only gave the first data point but then enforced the PDE constraint? Would we solve the PDE?
Yeah, so if you only gave this initial condition up here and then predicted the rest of the PDE?
Yeah.
Yeah, I think it really depends on the problem setting. I think in a very simple problem setting like this one, I think that would work fine if you just gave the initial condition and then just optimized over the rest of the PDE, so you might not even need those training data points in the first place. But this setting doesn't do super well when you go to harder problem settings if you just do this kind of ad hoc approach. And so one example here is that in this case, only the training was done by only giving the initial condition and the boundary conditions, and then predicting a solution over the rest of the domain. And as you can see in this case, especially when you have very sharp features in your solution, this becomes a lot harder to capture.
Okay. I hope that answered the Pearson's questions. If not, Pearson, speak up, or let's move on.
Great, and feel free to ask questions throughout the talk. So that brings me to one of the main idea of this talk, which is really this idea of how do we resolve some of these underlying issues when we try to solve PDEs with machine learning. And there's a few key points here, I think, to keep in mind. So one of those points is that this idea of physical consistency or having an accurate solution, this is especially important at inference, so at test time, when we actually want to go use the neural network for some type of task or deploy it for some type of task. And the current approaches that I've mentioned, whether it's data-driven or you add this self-supervised PDE loss, there's no guarantee of those physical laws being obeyed at test time in particular. And so that's potentially posing a problem for how you would actually reliably deploy this. The other point is that these so far are all grid-based methods. So this means that your solution is over some type of discretized domain. And that means that you could have some type of error that comes up because there's some inherent error in that discretization. And it can also be expensive because especially if you're training with some type of PDE loss, it requires differentiating back through that if you're going to take derivatives, if you have higher order derivatives in your loss. And if your architecture is more complicated, that can start to get expensive to train. And there's also some other points here. So sometimes if you have some type of physical law and it's only approximately enforced, so this soft constraint added to the loss function, this can sometimes be hard to optimize over and tricky to actually get to converge. And again, you have that first issue that this type of approach doesn't guarantee any convergence at test time. And all of these issues all become particularly noticeable in limited data settings. When you don't have a lot of data, each of these issues really comes up again and again and becomes a bigger and bigger problem. So the general theme of this talk is really going to be about this idea of numerical methods that have been really successful historically at modeling complex systems, and machine learning that's been very fast and successful at these prediction tasks in a lot of different areas. How do we take both of these and get the best of both worlds when we develop the next set of methods for scientific modeling problems? And both of these have their limitations too. So numerical methods can be quite slow. Machine learning can be hard to get accurate or hard to generalize to new problems. And so we're hoping that by taking the best of both worlds, we can also limit the actual limitations of both of these approaches. And by combining both, the goal is perhaps we can get better accuracy with less data, as well as more robust methods downstream. And so the approaches that I'll talk about are some of the things that we've been thinking about and working on for exploring this intersection between numerical methods and neural networks. So for most of this talk, the problem setting that I'll talk about is solving PDEs that represent some type of complex system. So in this case, this is an example of Navier-Stokes equations. You might have some initial conditions like an initial vorticity, and your goal is to predict the spatiotemporal behavior of this system over time. And in these cases, because these are spatiotemporal phenomena or fluid problems that we know a little bit about, we can sometimes know that this might have some type of conservation of momentum, it might have some type of conservation of mass, and so on. So the first issue I talked about was this idea that physical laws are not imposed at test time, and this can be when it matters most to have that physical consistency. And this can also sometimes be useful to enforce these laws at training time, because that ends up actually improving convergence. This ends up helping a lot, especially in limited data settings. And so the first solution I'll talk about is implementing PDE-constrained optimization as a layer in a neural network to tackle some of these issues. So before, the neural network setup looked something like this, where you have some spatiotemporal points in your domain. You use a neural network to predict the solution, and you could train to either matching the solution loss over your domain. You could also add this differential equation loss for the PDE, so this soft constraint approach. And then to train a neural network, we would backpropagate through this loss function with respect to the weights of the neural network. And after we train the neural network, we can go test it on new problems. As mentioned before, there are some potential issues with this approach. And so the thing that we try to do instead is actually look at, can we have more control over these physical laws and enforcing these physical laws? And to do so, we developed this framework to add a PDE-constrained optimization layer to a neural network architecture. So this is a high-level overview, but I'll go into some of the important pieces and details. And in this case, this PDE-constrained optimization layer can be added on top of any neural network architecture. So the problem setting here is essentially differential operator learning, where we're trying to find some operator that maps some parameters here to some solutions U, such that that conservation law or that operator is enforced, and we know that it's going to be equal to 0. So what we do here is we take a neural network, so this is a neural network F, parameterized by some theta, and we want to map the neural network, the parameters of your physical system to B, which is a set of n basis functions. So our neural network is trying to do this parameter mapping. And we formulate this instead as we want to find some omega such that when you take this product of those basis functions with respect to omega, this is going to satisfy whatever your conservation law is. So this equivalency is trying to make an approximation to your solution U. And so what we do is we solve for this omega value using some type of iterative nonlinear least squares solver. So this could be LM, it could be Gauss-Newton, or whatever your favorite solver is. And this is done by sampling a set of spatiotemporal points on your domain. And after we solve this problem, the final solution operator prediction is reconstructed together with having solved for a reasonable value of omega with your numerical solver. And so you're then having some approximation for the solution using this approach instead. So this is giving you a bit more precise control over actually enforcing this conservation law, because you're explicitly using a solver to try to actually approximate that PDE-constrained optimization problem. So when you look at this setting, I went through essentially what's a forward pass of the neural network. But the issue is that when you run that solver, so you project your outputs of the neural network onto some solver, and that's the solver that you're running to now actually learn the PDEs more precisely. The issue is that when you take all of these steps of your solver, you still have to train the neural network somehow. And doing standard backpropagation, where you differentiate back through all of those steps, is really expensive. It's actually usually impossible because you run out of memory very quickly. And so to get around this issue, what we did instead is, so we looked at this problem and we see that what we want to do is the solver is run after the neural network to come to a solution. And if we want to actually train the neural network, we need to differentiate back, and we need to do some type of gradient descent on theta, our neural network parameters, to learn what the correct solution is. And so we use implicit function theorem and implicit differentiation, which I think is a really powerful tool when you're doing anything with combining numerical methods and neural networks. And what that does is you can formulate this differentiation problem in an implicit way. So what that means is that you don't need to differentiate back through all the steps of your solver. So you don't have to backpropagate through the whole computational graph that got you to that final point. You can just differentiate the last step and bypass all of those intermediate steps. And a lot of the details, you can check out the paper for a lot of the details on the full framework and the exact problem that you're solving. But this is essentially the trick that makes it possible to combine these two things together. So coming back to this and the full problem setup. So now we have this neural network architecture. We project onto this PDE-constrained optimization layer, which solves the optimization problem more precisely that represents our conservation laws. We use implicit differentiation to train the model. So what it means is that the forward pass of the neural network is decoupled from the backward pass of the neural network. And that allows us to train this whole thing end to end with both the neural network and the solver. And this means that the neural network is able to get direct feedback from the solver, so the weights can update based on this exact solve that happens in the PDE-constrained optimization layer. And then at test time, we can go ahead and run this neural network on a new problem. And because the forward pass of the neural network still goes through this layer here, it means that those constraints are more precisely enforced at test time as well. So here's a very simple example of when we first tried this out. So this was for a Darcy flow problem, very simple PDE where you have some PDE parameters, in this case, diffusion coefficients, and you want to learn what the PDE solution is. And so we ran this with a baseline of, we just add the conservation laws to the loss function, this soft constraint approach, which does okay, but it doesn't really converge that well, and it sort of plateaus at this point. And our new model where we implement this new layer, which acts more like a hard constraint, and you can see that it starts at a much lower point and then continues to go down. And this is on some unseen test set, so we just track how well it's doing during training on this test set. So it does tend to converge more quickly for a problem like this. But that being said, I mentioned that during training, you're going through this new layer and differentiating it, but also during test time, you also have to go through that new layer. And what that means is that as you enforce this layer and this whole setup on more and more points, which can happen or is quite necessary when your problem gets quite hard, that also means that your computational expense and memory cost increases. So this is an example of solving the 2D Navier-Stokes equations. So as we increase the number of sampled points, it's likely that the model does better because it's able to solve for a larger domain and force whatever physical laws over a larger domain. But the issue is that as you increase these points, both your training and your inference time get larger and larger. So there's this limitation of the computational trade-off. And if you sample more points in this setup, you often need to have a lower batch size because of the memory costs, and that ends up actually hurting training stability. So for some of these much harder problems, it becomes very difficult to solve with this current setup. So to get around that setting, we used a mixture of experts approach to actually scale this full architecture. And mixture of experts really has made it possible to scale a lot of very large models in many other fields of machine learning like NLP and vision. And it's this nice way of actually increasing the capacity of the neural network, but still balancing the computational expense, where now you split the computation over a bunch of different experts that solve these different subdomain problems. And so we wanted to see if we could actually bring this idea of mixture of experts to our physical modeling problem and actually be able to scale it to much harder systems. So we frame this PDE-constrained optimization problem in our neural network as a mixture of experts instead. And the main difference is before we had this neural network, this f of theta, and we would go ahead and go straight to the end here and run our solver, do our prediction. And this time we actually split our domain into a bunch of different subdomains and use an expert to solve the problem along each subdomain. So what that fully looks like is you have some type of neural network here. We use a neural operator for this type of problem. It doesn't matter which architecture you use, though. It could be your favorite one. And this whole part here is our PDE-constrained optimization layer. And to scale it up, we do this domain decomposition where we have a bunch of different subdomains. And we enforce this constrained optimization problem over each subdomain. So these are the hard constraints that are enforced over these subdomains by the different experts. And so this makes those constraints localized, and it's split across multiple experts here. So it's not just one single one, but many different ones. And the advantage of this is that now we've actually decomposed our domain and we can actually solve this problem in parallel. So when we put it all together, if we have some PDE domain, I've kept it very simple here, just a 2D problem, but we also do this on 3D and 4D settings. You can give this PDE domain to the neural network, and it'll go through this whole process of you have these learnable basis functions here. You evaluate and partition them over your subdomains. You have this mixture of experts setting where each expert locally solves the problem. And so it looks something like this, where within each expert, you're still doing that same task of finding a set of omega that satisfies this product here and actually satisfies the PDE of interest. So it's the local constraint over each subdomain. And then you can go ahead and reassemble your full predicted solution together. And then putting it all together, you go ahead and differentiate your output, and then you use implicit function theorem to actually train the full model end to end. And when you do this, that means that each expert is both being used in the forward pass, but also in the backward pass through this implicit differentiation technique. So this allows you to actually scale the model and train it over a lot of different problems, because everything can also be done in parallel now. So as an example of what that looks like, this is a problem, a diffusion absorption problem. It's a tricky problem actually, because it has a singularity at a certain point here. And this is what the numerical solver solution would look like. And if you're using a soft constraint approach, because of some of those difficulties, you can see here that in a lot of cases, it's not really able to converge to any solution. So when we use our initial approach where we just have a hard constraint, we start to do a little bit better, but I think it's limited to some extent because you need to sample a lot of points for this problem. And because we can't fit all of those points, we often have to use a lower batch size, so it actually hurts our training stability. But when we go ahead and scale this with this new mixture of experts approach, we get a lot closer to what the true solution should be, so it starts to match the numerical solution pretty well. Another advantage is this idea of lacking training stability. So when we actually train with our regular layer with no mixture of experts, it's not doing super well because of the fact that during training, it's unstable, and it's not just because of this limitation that it can't sample enough points because of computational expense. But when you actually then train with this MOE setting, this is another sample that was pulled out of this system. So we had a test set of a few hundred samples. In this case, when you actually train with that MOE setting, you're a lot more stable and predictable when you're doing the training. So it's converging slowly to the right solution in a more stable way. And then when we come back to this plot where we saw that one of the limitations before was that as you increase the number of points, your training and inference time gets slower and slower. In this case now, when you increase the number of points, this scales sublinearly. So this is a lot more efficient. And I think this is quite important because as we get to the whole point of neural networks is to be faster than numerical solvers. And at inference time in particular, if running a neural network is slower than running a numerical solver, there's not really much of an advantage to the neural network approach. So getting this down to some level of computational efficiency and speed, I think, is very important for actually the whole purpose of using neural networks. So I'll come back to some of these underlying issues that we looked at earlier about solving PDEs with machine learning. And the second big issue I had mentioned was this idea that grid-based methods introduce errors. So when you solve for a solution over a discretized domain, that's going to inherently introduce some errors. And so one solution that we thought of when we looked at this problem was, again, an idea of taking spectral methods, which have been really successful, used quite well in applied mathematics and scientific computing, and seeing if we could take the advantages of spectral methods and combine that with the advantages of neural networks. So coming back to this setting of this physics-informed neural network loss, so this would be like a self-supervised setting for solving PDEs. So when you optimize over this PDE residual in the loss function, there's this first point that you're optimizing over physical points in your domain. So those grid-based methods introduce errors. It can also require a large number of sampled points. So if your problem is hard, you may need a lot of points to optimize over. And so this approach also just has issues with scaling to large grid sizes. And finally, if you're looking at this setting where you're using a neural operator and then optimizing over it with some type of PDE loss, this can be expensive to differentiate back through the architecture, especially for more complicated architectures like the Fourier neural operator. It means that some of the scaling actually doesn't do super well, especially if you have higher order derivatives that you're trying to enforce. So spectral methods have been very powerful for solving PDEs. So these basis function expansions, you could use Chebyshev polynomials as one example. You could use Legendre polynomials. They can be quite powerful and efficient. And when you're learning PDEs in this spectral representation, you can really do accurate approximations of differentiation and integration, or you can really do accurate approximations of algebraic operations going out to a certain, when you go out to a certain number of terms when you do that basis expansion. And so I think these have a lot of potential to also think about how they can be integrated with neural networks, because there are so many advantages of these methods in the scientific computing setting. And so to take the ideas from spectral methods and neural networks and really get the best of both worlds, we came up with this neural spectral methods approach, where we have in our base architecture some type of spectral based neural operator. It's not just limited to Fourier basis, so you can actually use Chebyshev polynomials or Legendre polynomials, so really any spectral basis function. And we actually find that for a lot of the problems we look at, using Chebyshev basis actually works a lot better than a Fourier basis, particularly in cases where you don't have periodic boundary conditions as what you would expect for when you see how where they're used in scientific computing. And we also have this spectral loss function, and I'll go through each of these. And this is in contrast to this idea of physical space learning that had some of the limitations mentioned before, that it could be harder to learn and you have these grid size limitations. So we start in this case in our base architecture by we have parameters to solutions. This is the same setting that we want to learn. And we look at the spectral representation of our parameters. We do these spectral transformations. So this is where we're deciding what basis functions we want to use. In this case, Chebyshev polynomials tend to be the ones that end up working quite well. And then for the last point, we use this spectral training procedure where we can actually use Parseval's identity to come up with an equivalency between some type of PDE loss in your physical domain and what that spectral representation is, because you can have this equivalency through the sum of the square of your spectral coefficients. And that essentially gives you a very good approximation for what the PDE residual of the problem is. And what that means is that you can actually not just project to spectral space and do all of your architecture transformations in this part of the architecture. You can then train the whole model fully in spectral space by using this spectral loss function. And that allows you to just do everything in the spectral domain, which will have some advantages, as I'll talk about now. But just a quick note is that this is in contrast to training in the physical domain if you have some grid-based neural operator. and you have this PDE loss, or this physics-informed neural network loss. So this would be, so the top part is the spectral approach in contrast to this physical approach. So here's one example where we looked at a reaction diffusion system. So in this case, we have, this is just a 2D problem. You have some temporal dimension and some spatial dimension. And we ran a numerical solver on this. So you see that it behaves very predictably. As you increase the resolution of your domain, the error gets lower and lower. And this error is relative to a very fine discretization. So we generated a really fine solution, and then we subsampled it to represent all of these different grid points. So if you use this approach of a standard grid-based neural operator, and you add, and then you add some type of PDE loss to that, so this would be training only in physical space, you can see that it doesn't quite match up super well. So it's slower with a finer discretization. And one thing is that you can see that it actually overfits a little bit to the training grid that it was trained on. So it actually sometimes will do worse for higher training grids rather than decrease continuously like this standard numerical solver. So this would be like the grid-based approaches. And in contrast, when you do this all in the spectral domain, so you use the approach I talked about where you have this neural network, you train it with a spectral loss, you end up down here for all of your grid sizes, because now the grid no longer matters because your computational cost is constant regardless of the grid size, because you're actually not expressing your loss function in terms of the grid itself. So there's no sampling issue here. And you can see that it maintains accuracy. So when you compare it to this standard numerical solver, it's faster for the same level of accuracy, which I think is the comparison that we should be doing for all new neural network methods in this ML for PDE space. We also went and looked at different forms of the Navier-Stokes equations. So this is an example where we're looking at unforced Navier-Stokes equations, where the top row is our numerical solver. The middle row is our method, and the bottom row is when you train only in physical space. So this is actually an animation, but we converge pretty quickly with this spectral approach. Whereas when you look at the bottom row, there's a lot of features here that just don't converge to what the numerical solver looks like, and these are somewhat hard to resolve. And this is another example where now we look at forced Navier-Stokes equations. So we have this numerical solver, we train only in physical space, and this actually blows up over long time scales. So the error gets really high as you get further and further away in time. And when you do this approach with spectral methods, it's a lot more well-behaved. So over time, the total relative error ends up being a lot lower. And I didn't plot the computational speed here, but that's also a very big advantage of this approach, that it's a lot faster both during training, but also when you actually go and use this model during inference. So the last thing I'll talk about is, so far I've talked about this idea of inspiration for numerical methods and neural networks in the context of solving PDEs, so fluid dynamics problems or other general types of PDEs. But I think these simulation in the loop ideas can also be really relevant for other problems like molecular systems or things at the atomistic scale and running molecular dynamics. So this is an approach here where the way you train models for molecular dynamics, a very common approach is that you try to approximate the potential energy surface of these systems. And if you have a good approximation for the energies and the forces, you can then run these simulations over time by using a numerical integrator. And hopefully you can run it for very long time scales without it running into instabilities, because then you can study the system better. You can compute observables about the system from that type of simulation. But there are also some challenges here. So this is an example of a neural network trained for these molecular simulations. And we go ahead and run this over in time. So we simulate the system over ideally long time steps. And initially it seems okay, but as you simulate the system longer and longer, you see that there's this very clear unphysical thing happening where there's this bond stretching that results in a very unstable structure. And both what that means is that, so you can't really trust the simulation because there are these instabilities coming up, but any types of properties that you then want to compute from that simulation are probably going to be very inaccurate because the simulation is just not stable enough to get to the point of where you can do those computations. So coming back to the idea of simulation in the loop, there's a lot of learning signal that you can get from the molecular simulation itself. So in this case, this approach, it's a slightly different problem setting in that you might have some atomistic system, some molecular system. You give it to a neural network and you predict the energies and the forces of that system. And once you have the forces, you can use numerical integration to get to your next time step. And this is how you would run the simulation over time. And as you run this MD simulation over time and keep running it, you can compute system observables about that system. So something about that system or multiple properties of that system. And so typically the common approach to train these models is to train this neural network to just the energies and forces. But in this case, we wanted to actually train the neural network to the simulation itself. So actually use all of this information of the simulation and build that into the training procedure somehow, because that would also then allow us to train to more than just energies and forces. We could actually train to observables of the system. Maybe those observables come from experiment. So this could be actually a way to bridge some type of theory experiment gap as well. And so the same idea here is when we go and train to these observables over MD simulation. So we run the MD simulation, we query the neural network, run the integrator, we compute system observables, and we take a loss function on the observables. Now we come into the same issue that we had before, where you can't differentiate back through all of the steps of your MD simulation, because it means that you're going to differentiate through all of the steps of your numerical integrator. And so instead here, we can do the same thing. We can train the neural network with implicit differentiation. So there's actually a way, it's a different approach to formulate this implicit differentiation problem than the previous approach I talked about, because this is actually a stochastic setting. So you're actually doing implicit differentiation over a distribution. But the key idea here is that you can formulate taking the gradients this way. And the key insight is really that you separate getting the neural network output from the rest of the neural network itself. So you don't have to backpropagate back through all of the steps of the solver to get there. And so this ends up also being quite powerful in the context of molecular dynamics. So this is an example of a water system, and there's a local instability that comes up. So the full simulation in the loop method and the differentiation technique, we call this a Boltzmann estimator, because we formulate the implicit differentiation problem based on the fact that we know that the underlying system obeys a Boltzmann distribution. And this is how you can actually formulate what the differentiation task should be. And so before training, when you use standard training, so the approach over here, where you just train it with these energies and forces, when you run this system over time, over all of these picoseconds, all of the trajectories become unstable relatively quickly, so often too quickly before you can actually compute things that are of interest, so observables of interest about the system. But when you actually now train it in this simulation in the loop style, after we do our training procedure, we can actually simulate this system for, we went up to 1 nanosecond, but you can also go further than that. And you can see that the system no longer has the same instability problems as before. And the way that this nicely manifests is that if we then want to go and actually compute things from the system, so in this case, we don't train it on anything about the diffusivity coefficient. So it doesn't see anything about this. But after we train it with this procedure and we go run it at test time and we compute the diffusivity coefficient of the system, we end up being a lot closer to what the true coefficient is. So this black line here represents the reference. And before training all of these, before our training, the trajectories were not really getting any close to those reference observables. And after our training, we're a lot more in the ballpark or in the general range of what that true diffusivity coefficient should be. And so I think this type of procedure is powerful for both bridging this theory and experiment gap, but also the fact that by doing this procedure, you can improve both the stability and performance on new systems or new observables and actually have some level of hopefully more reliability in running those molecular simulations downstream. And the very high level general idea of bridging numerical simulations with neural networks is still generally true here in this setting as well. So in summary, I think neural networks do have a lot of potential for these physical modeling problems. But at the same time, we really need to keep in mind this idea that we need accurate and rigorous methods that are going to be able to give us reliable, physically consistent answers when we go run that method in a simulation or go run that neural network in a simulation. And this idea of also having trust during deployment. So after we train a model, we would like to trust it when we actually go use it for a lot of different downstream tasks. And so here I talked about a few different examples of the best of both worlds. So taking numerical methods and deep learning and putting these together with this idea of differentiable solvers. So ways to actually come up with differentiation techniques that let you train these two things together. So whether that's through this idea of a PDE-constrained optimization layer in the neural network, or taking neural networks and combining them with spectral methods ideas, as well as the fact that these simulation in the loop ideas also extend to problems like molecular dynamics, where it's a bit of a different setting because you have a stochastic setting, but you can still formulate the same differentiation approaches and train this model to the output of a simulation itself, and ideally improve the simulation stability as well as the accuracy of the properties that you compute from that simulation. And the papers with all the code available for everything I talked about are all down here. So you can definitely go check it out and let us know if you have any questions. And finally, I'd like to thank a lot of the great students that I get to work with. So a lot of the work I talked about here was with Yiheng, Nithin, and Sanjeev on all of these different areas. And I'll go ahead and come back to this summary slide and happy to take any more questions as well. Thanks.
Awesome. Awesome. Thank you so much for the wonderful talk. Very nice. Okay, there were questions during your talk. So the first question is by Gijo. She wants to know about what kind of neural network you used in slide 8.
Sure. Yeah.
I think that's when you talk about the pins.
Oh yeah, I think slide 8. Yeah, that was just the toy example setting. In that setting, it was just a simple MLP for that problem. But in some of the later methods settings I showed, we used a few different types of neural operator architectures. But the methods I was talking about, a lot of them are agnostic to the underlying architecture. But in that toy example, it was just a regular fully connected neural network.
Okay. And second question is by Fedi. In slide 45 and 46, how would the spectral methods work when the flow has discontinuities, for example,
Yeah.
shocks?
Yeah, that's a really good question. So how would you solve a problem if there's any discontinuities? That's actually exactly what we're working on right now. So we have some ideas that there are potentially ways that you could parameterize your domain with maybe like using something analogous to finite element methods. And that would at least help with the fact that you would have discontinuities in your domain. I think it's a really good and a very important problem, especially if you're looking at systems with complex or varying geometries.
Okay, next question is by Sakar. He has a bunch of questions. Do you mind, Sakar, unmute yourself and then ask that question yourself? If not, I can ask. Okay, his first question is there a reference for implicit differentiation applied to these applications? The neural net plus the numerical solver. That's his first question.
Yeah, for these areas, so some of the earlier work in this area, there was this idea of OptNet or optimization as a layer, which was this very general approach that maybe you could incorporate some type of optimization problem into neural networks. And there's also been approaches like using the adjoint method, though that's not, I think, quite in the same flavor as a lot of the work that I talked about here. And the adjoint method actually can have numerical instability problems that don't come up in the same way for in the settings that I talked about here. For in the context of using implicit differentiation for example, solving PDE problems, I think the reference would really be like some of our work here, where we, in this first paper, we actually formulated doing this as a PDE-constrained optimization problem, and then extended it to the MOE setting.
Okay, and his second question is, can the computation by each expert in the MOE method be parallel?
Yeah, exactly. Yeah, it can definitely be parallelized. So that's one of the big advantages, that you're not just solving the problem on a bunch of different subdomains, but you can do that computation on all of those subdomains in parallel. So that's also one of the reasons there's a big speed up in doing it with the MOE setting.
Okay, the last question by Sekar is, how much faster, slower is the method MOE compared to a numerical solver for inference?
Yeah, compared to a numerical solver for inference, for the settings that we looked at, so we started looking at a few different settings: diffusion, sorption, reaction diffusion problems, Navier-Stokes problems. With the MOE setting, we are faster than a numerical solver. In the original setting that we had, where we didn't use the MOE, we were about equal with the numerical solver at the time. So the MOE was actually quite crucial to being faster. That being said, when we first did this, it actually wasn't super optimized to run these iterative solvers on GPUs. That operation was actually not super well optimized for the in this context of actually trying to do optimization directly there, because you have to do it on the GPUs if you want to train it with a neural network. Since then, there's been a lot of improvements. So I think actually at this point, even without the MOE setting, I think we actually would be faster than the numerical solver for a lot of problems, but you get a much bigger speed up, and the more practical version of this is to do it in the MOE setting.
Okay, next question is by Mike. Is there communication in the parallel solve at the domain boundaries?
Yeah, that's a really good question. So how do you deal with the fact that there's a domain decomposition and there could be issues between the boundaries? So what we actually found there was that as long as each expert, so each subdomain solve, had the global initial and boundary conditions, that was actually enough for it to learn something reasonable and not have issues at the boundaries. Before we gave those global conditions, we were doing some things like trying to actually have overlapping domains, like stitching the boundary conditions, doing some type of Gaussian smoothing over the boundary conditions, or over the boundary conditions of the different domains. But just giving the global initial and boundary conditions to each subdomain ended up actually solving that issue.
Okay, next question is by Kwan Chon. Nice talk. You've shown strong advantage of neural spectral method. Perhaps he missed it, but are there any deficiencies to the method?
Yeah, so for deficiencies for the method, so I think one was the point that was brought up earlier. How do you deal with discontinuities? And so this is something that we're, like I mentioned, we're actively working on this and using approaches to actually deal directly with discontinuities, especially if you have very complex domain geometries. And so that's one approach. The other approach is also that sometimes you might need more frequency modes to actually really capture the domain, especially for some of these more complex problems. And so you have to be careful there, because there's that trade-off of more modes means that you have some computational inefficiencies. So it's going to be slower to train the model or run the model. But that's also something that we're actively working on now. And actually, we've already made some speed ups, which will be pushed to this repository pretty soon, that deal with that computational inefficiency problem.
All right, Kwan Chan also asked, can you recommend a good reference paper on MOE theory?
Yeah, for a good reference paper, so one of the earlier papers, I think with Noam Shazir from 2017, that's a good starting point for one of the earlier examples of something that worked quite well. But if you want to go even further to the theory, there's papers from the 90s that describe the problem setting. But that 2017 paper is an example of showing it in action in large-scale machine learning.
Okay. Next question is by Mike. If you run the new approaches, can you show that you can run these problems out indefinitely without an instability?
Yeah, so is that in the PDE setting or like the molecular dynamics setting?
Probably PDE setting, I'm sure. Yeah, PDE, yes.
Sure. Yeah, so we haven't tried running it out indefinitely, so to speak, just running it for uh, months and months at a time. I think this does definitely help stabilize the method so you are able to do these much longer rollouts. And this is actually something we've started testing a lot more now. So we are able to run some of these Navier-Stokes systems for longer timescales. But I think this also comes into, as the problem becomes harder and harder. So if you have turbulence flow, for example, you have really high Reynolds numbers, I think that's where long time scales becomes hard. And I think that's actually one of the big challenges that we should really be working on with these methods to see how well we can do that long time scale modeling.
Okay. Next question is by Shutong. Does the network approximate the coefficients of the basis function for the spectral method? If so, will there be an error when transforming the field from the physical domain to the spectral domain? Will this error propagate during the time domain evolution?
So it sounds like the question is, so you're operating on spectral coefficients and you're training specifically in spectral space on those coefficients. So the nice thing about the spectral approach, and I can go back here. So this identity here, so Parseval's identity essentially gives you an exact form of the PDE residual up to a certain amount of basis functions. So whatever you truncate your basis functions at. And so this is computed directly with the sum of the squares of your spectral coefficients. And so because you can actually do this as an exact computation, this actually ends up not really mattering that much because you've effectively solved for the PDE residual in a mostly exact way up to a certain level of basis function expansions. And so that issue doesn't really, or we found that issue doesn't really come up when we actually use this neural spectral methods approach on a physical problem, that when you actually translate this to solving on a physical grid, it ends up being the same either way.
Right. Related question by me, but it is that accuracy of the spectral method, neural spectral method, is bounded by whatever the spectral, the basis you are using, right? I mean, if the spectral basis can capture like 99.9% of your solutions, then you're stuck with it. That's the best you can do.
Right. It does depend on what spectral basis set that you use, but we're also exploiting the fact that as your basis expansion goes towards infinity, it means that you're in theory going to be able to exactly approximate the solution.
Yeah, in theory, yes. But in practice, you have to truncate at some point. You cannot go infinity. So there will be, the limitation in accuracy, how much you can represent with the spectrum.
Yeah, so we found, at least in the settings I showed, and we're now testing it on harder settings, that we didn't have to go towards infinity or something to a very, very large number of terms. Usually we could go within a reasonable amount, within a reasonable computation cost, and get most of the way there.
If there is no shock or discontinuity in the solutions, yes.
Right, exactly. If there's no shock or discontinuity, and that area now we're actively working on with a few other approaches. Yeah, definitely agreed.
Another question by me is, nonlinear manifold reduced model, like the projection-based reduced model, but you introduced the nonlinear manifold, the neural network kind of basis solution representations, and you plug that into the, existing numerical method. and solve for the latent space coefficients instead of the full space, so that, you get the efficiency. The method you introduced, so-called the physics constrained method, the first method you introduced, it has a very similarity between those two, by the fact that you do take advantage of the existing numerical method, and instead of the traditional basis, you use the neural network basis, and then you actually solve that PDE, right? So yeah. So my first question is, are you familiar with that nonlinear manifold reduced to the model?
Yeah, I'm familiar with that general area, and I do agree that I think there is some overlap in that. I think some of the advantages of both the approaches I talked about here and that approach are that you're doing a change of basis and potentially now learning in a space that's going to be easier to learn on than it was before.
Yeah. So, but in that projection-based reducer model, because you're introducing more nonlinearity through the neural network you just introduced, which was not there before. So the complexity of the nonlinearity has increased. So because of that, it is very important to, apply the technique, so-called the hyperreductions there. Otherwise, you wouldn't get the speed up, because you're interacting with the existing numerical method, and you have increased the nonlinearity in very intertwined way. So you do need some special method to deal with it. I'm wondering if for your method, if you need those kind of, how do you handle the nonlinearity you introduce through that neural network?
Yeah, I think so I think in practice we haven't seen that be a big issue. At one point we were using much more complicated iterative solvers because we thought that that would be the one-to-one between solving this in a numerical setting and solving this in the neural network setting. But as long as we just have a reasonable iterative nonlinear least square solver, we found that the neural network would do the rest of the heavy lifting. And so we didn't explicitly see, I think, this issue that you're describing, but I think it's definitely interesting, and it would be worth testing out on more cases to see if this actually explicitly needs to be dealt with.
Okay. All right. Well, it's 3 minutes after 11, so I think it's a good time to finish our, your seminar. Thank you so much for the wonderful talk and beautiful introduction of those 3 methods, and yeah, definitely more interested in going too deep and then learn more about it. So thank you so much for
yeah,
nice
thanks a lot
talk.
for all of the great questions. It was fun to have so many questions, and feel free to contact me afterwards if you want to talk more or have more questions.
Awesome. Thank you, Aditi.
Great. Thanks.